All right, you guys, welcome. So in this section, we're actually going to graph the polynomials. In 4.1, we talked about end behavior and the multiplicity of zeros, so we could see if it crossed or was tangent. And so now we're going to be able to learn a few more things, and we're going to be able to end with sketching these polynomials. Okay, so one thing that we're going to talk about right now is turning points. So a turning point of a polynomial is where it changes from either increasing to decreasing. So we would call this a turning point, or where it changes from decreasing to increasing. So this could also be called a turning point. Okay. And it says up here at the top that where a turning point is either going to be a relative maximum or a relative minimum. So for example, this would be a relative maximum. This is a big deal in calculus, that we know that where it changes from increasing to decreasing gives us a max, and from decreasing to increasing gives us a min. Okay, so these are going to be turning points. All right. Okay. So there's a kind of a formula for turning points. If the highest degree of the polynomial has degree n, then there's going to be at most, make sure you see that, n minus 1 turning points. So let's look at some examples to help you kind of remember this and see that this is true. Okay. So for y equals mx plus b, we know that that's a line. And if we look at some lines, I'll just give you a few examples. Okay. Let's say we have just, some stock line, some standard line here. We can see that that is degree 1, right? Well, let me back up a little bit. This one has 0 turns. There's no relative maximums or minimums. This has 0 turns. Same thing for if I have just like, maybe let's do a horizontal line just to be different. There's not going to be any turns in that. So what we can conclude is this is degree 1. Degree 1, and that there's 0 turns. Okay, so we can notice the difference. The difference here is that this number is 1 less than that number, right? Okay. All right, let's come over here and look at something to the second power, degree 2. Okay, let me give you a couple of pictures for that. Oops, I meant for this to be black again. Give me 1 second. Okay, so degree 2 polynomials, quadratics, are parabolas, right? So maybe, your standard x squared, maybe some downward facing parabola. Okay. And so now we can see we actually do have turning points, right? We have one turning point. All right, so the degree for this was degree 2. And the turns, well, there was 1. So we still have this idea of 1 less, right? Okay. So this up here where it says if it's degree n, it has at most n minus 1, 1 less is really, we're seeing it, 1 less than 1 is 0, 1 less than 2 is 1. Now let's go and look at it more complicated, because we haven't looked at this at most yet, right? So let's go ahead and take a look at some different graphs for some cubics. Okay, I'll just put a couple graphs in here. Okay, so maybe, a cubic like so, but also x cubed. Okay, all right, so we know this one. This was one of our parent functions that we memorized, right? X cubed. Now this first one has 2 turns, right? This one technically has 0 turns. That spot that I highlighted is not a turn. Okay, it's a shelf point. It doesn't change from increasing to decreasing. It's increasing, 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 and still increasing, increasing, increasing. Okay, so that is not going to be considered a turn. So this was a degree 3 polynomial. Oops. Degree 3 polynomial. And then the number of turns that we got, well, one was 0 and one was 2. So this is why you can see, well, it's not always one less. Like this is 3 and this one's 2, that matches. But we have this 0 here. And so that's why the words at most n minus 1 are important, because it might be that it's not necessarily one less. It could be any number less than 3. Any number less than 3. Okay. All right, so hopefully that clears it up and kind of helps you remember if it's on a quiz and you're like, okay, well, let me think of a parabola. It's degree 2, how many turns? 1. You know, so you remember that, one less, at most one less. Okay. Determine the maximum number of turning points and verify it with the graphing utility. So we're going to go through these super quickly. Okay, the degree for this is degree 3, right? So that means as far as the maximum number of turns, but it's going to be one less, right? So this would be 2. So let's go ahead and verify it. Now, we're not saying it is 2. It could be 0, 1, or 2, right? Okay, so let's go and look. So we're going to grab this. Let's pull up good old GeoGebra. All right, let's see here. This is x to the 3rd minus 21x plus 20. All right, let me just zoom out so we can see it. I'm gonna have to zoom out the y-axis so we can see it. There we go. All right, so I'm gonna go ahead, snap a picture of this guy and bring him back. But you can see already, as I'm taking a picture of this, that this has 2 turns, right? Let's highlight them. And that goes along with what we said about a maximum number of 2, right? Perfect. Let's try another one. All right, so this one is degree 4, right? The highest exponent is 4. So we know that the maximum number of turns is 1 less. So it should have at most 3 turns. Let's go see what this looks like. All righty. This a little bit bigger. There we go. Okay. So this one is x to the 4th. Let's delete this guy out. X to the 4th. Oh, sorry, negative 2x to the 4th. Plus 3x to the 3rd. All right. And I'm going to actually make the y-axis a little bigger so we can see all those little movements. And let's stretch out this way too so we can really see it. There we go. Okay, so let me snap a picture of that. We'll bring that back. Okay, so what we said is we said at most 3, right? There we go. You know what? I'm gonna have to undo all this. I think I accidentally grabbed too much. There we go. All right. Take 2. Sorry, you guys. Okay. All right, so this one is supposed to have at most 3. It actually only has 1 turning point. Okay, this right here is not a turning point. That's a shelf point again, because we're increasing, 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 stop, and still increasing. Remember, it has to change from like increasing to decreasing or decreasing to increasing, which it does here, right? Increasing, increasing, decreasing. So this one only has 1 turn, but that fits the bill because we said at most 3 or maximum number of 3. And so this looks great. All right, now we kind of have another rule for the x-intercepts. So it says, the graph of a polynomial function of degree n has at most, so it's at most again, n real zeros, and thus at most n x-intercepts. So it could be that it has less than n real zeros, okay? All right, now it matches, it's not 1 less. If it's degree n, it'll have at most n. So that's kind of tricky. You've got to make sure that you think about that. And so let's go ahead and dive in and really think about what that's saying, okay? if we go back and we look at pictures of lines again, right? Maybe I could even use those same exact lines. So if we look at the x-intercepts, that one has 1, right? 1, 0, 1 x-intercept. But if I graph this one that I graphed earlier, this one actually has 0 x-intercepts. So the degree was 1 because of the exponent being 1. Okay. And as far as the number of zeros or x-intercepts, make sure that you understand that those are interchangeable, right? Okay. That could be at most 1, right? At most 1. These actually match now, right? Let's take a look at some quadratics. So we'll do kind of the same examples as last time. We could have, actually, I want to do 3 examples for this, you guys. Let me kind of draw these again, make sure I can fit 3 in. Oops, fit 3 in here. All right. So I could have a parabola that comes down and just nicks the x-axis at one spot. So that's going to be 1 x-intercept or 1, 0, right? Maybe my parabola doesn't even touch at all. It's up here, faces upward, and is above the x-axis. Or maybe it comes down, hits once, and then hits again, and it ends up having 2 zeros. 2 x-intercepts. Okay. So this one is degree 2. A parabola is a degree 2. That's our highest exponent. But as far as the zeros / x-intercepts, right? At most 2. I don't have to have 2, but at most 2. All right, and our last example that we're going to look at is a cubic, right? So cubic, let's see what that looks like. So I'm going to do 3 graphs for this one as well. Okay. All right. So if we draw some cubics, cubics often look like this. Okay. And this graph right here would have 1, 2, 3 x-intercepts. The cubic, if I do that same cubic, but I just shift it up a little bit, like it hits, it comes down and is tangent right here. It doesn't cross. Boy, I'm shaky on that one. So crosses come down tangent. That wasn't much better, you guys, but I'm going to leave it. All right, so that one's going to have 2 x-intercepts, right? Or the x cubed graph. That one actually only crosses 1 time, right? So we can see that a degree 3 polynomial, as far as its zeros / x-intercepts, it has at most 3. Okay. All right, so hopefully these first 2 theorems, that the turning points is at most 1 less, and the x-intercepts is at most n, the highest degree, can kind of make sense. Determine the maximum number of real zeros, verify with the graph. Okay. All right, so we can see that the highest exponent here is 3. So this is a degree 3 polynomial, which means it's going to have at most 3 zeros or 3 x-intercepts. Okay. So if we take a look at its graph, this is going to be x to the 3rd. Let's go back to algebra. All right, so this is x to the 3rd minus 21x plus 20. Okay, so I'm zooming out until we can see this guy. All right, that's enough because we just need the x-intercepts this time, right? Actually, maybe I can get this just to get a better looking graph. There we go. All right, so let's go ahead, put this on our screen here. All right, so we said at most 3 zeros, 1, 2, 3. It looks good. Okay, let's go look at the next one. So this one is a degree 1 polynomial, a line. So our claim is it's going to match. So at most 1, 0 is our answer. And we could probably graph this one on our own. We don't even need, let's do it. Let's graph it on our own just because we're pretty good at this. So we know that the y-intercept would be 3. So 1, 2, 3. That would be our first dot. And then our slope is 2, right? So that means we could go up 2 over 1. Since I'm trying to get zeros, though, I'm going to go down 1, 2 over 1. And then down 1, 2 over 1. So here's our line. So it's just going to cross in one spot, right? Okay, not drawn very well, but you get the idea of that it only has 1, 0, right? All right. There we go. Okay, so let's go ahead and take everything we learned in 4.1, end behavior, zeros and their multiplicity, and all this stuff. And let's go ahead and sketch some polynomials. So I'll read through this. We're not going to maybe do all 7. My thing is, let's just do enough to get a sketch of the picture, okay? But let's read it anyway. So use the leading term to determine the end behavior of the graph. We'll definitely do that. Determine the y-intercept. We'll definitely do that. Find the zeros and their multiplicities. We'll definitely do that. So 1, 2, and 3, we're doing every time, okay? 1, 4 also. Plot the x and y-intercepts and sketch the end behavior. Now these, and 5 will do also, okay? So remember the multiplicity. If it's even, we'll just have to be tangent to the x-axis. If it's odd, we'll cross through the x-axis, okay? 6 will come up on one of our examples today. It doesn't come up often, but when you can spot it, it's nice. And then if you're like unsure, if you're ever unsure, like how to make your graph go through the points, then just plot more points. You can always plug in x values and get y values until you start to get more and more accuracy, okay? I'm going to tell you, I'm not super concerned with like really detailed accuracy. I just needed to have the general shape and have some key things in there that are showing, okay? And trust me, this will be enough to get you through calculus, okay? So I'm kind of keeping that in mind as I'm thinking, well, how detailed do we need to be, okay? All right, so it says sketch the function. All right, so let's go ahead and do number 1. So number 1 was the leading term test, right? So the leading term, if we were to multiply this all out, right? Okay, so let's say that we have x plus 1 squared, right? So we have it twice. I'm not going to FOIL this whole thing out or multiply this whole thing out. That's unnecessary for me to do that. But what I'm going to say is if we multiplied all the fronts, then the leading term would be x times x times x times x, aka x to the 4th plus that I don't care about. Let me put plus dot dot dot. Plus dot dot dot. So the leading term would be x to the 4th. So that means the leading coefficient would be 1. Now remember that front number, that 1 that's in front, that tells us what the right is doing, right? And since it's positive, that's going to imply that the right goes up. So right with an up arrow. Now the degree of the polynomial tells us, it's degree 4, that tells us what the left is doing. So since it's even, that implies the same. So whatever the right was doing, the left is going to do also. So if the right goes up, then the left goes up. All right, so we have our end behavior. All right, so now let's go in and get, for number 2, the y-intercepts. So remember, for y-intercepts, you let x be 0, okay? So we're going to substitute a 0 in for the x's in the original problem. So let's find f of 0. So 0 plus 1 is 1. 0 minus 2 is -2. And 0 plus 4 is 4. 1 squared That's just 1. And then -2 times 4 is -8. So when we multiply that, we get -8. So that means that 0, -8 is on the graph. So I'm going to start sketching some things, okay? So let's pretend this is -8. We know we have a point right there, okay? All right, now let's go ahead and go in and get our step 3 x-intercepts. So we know for x-intercepts, we let y be 0. In other words, f of x. So we're going to substitute a 0 in right there. And we're going to find all of our zeros. Now this one's already factored. We'll work our way into ones where we have to factor, but we just set each piece equal to 0, right? Each factor equal to 0. We don't need their exponent. Their exponent is just telling us the multiplicity of that 0. So we have x equals -1, and that's going to have a multiplicity of 2 because of its exponent being a 2. The rest are 1s, right? So when we write down these zeros of x equals 2 and x equals -4, these are going to have multiplicity 1. So remember, if it's even, it's going to be tangent to the x-axis. And if it's odd, then it's going to cross through the x-axis. This should be enough to get us what we need, you guys. All right, so I'm going to mark the zeros. -1 is one of our zeros, so I'm going to go ahead and mark that. 2 is one of our zeros, so let me mark 2. And then -4 is one of our zeros. Okay. All right, didn't make that 8 low enough, but I think we can still make it work here. All right, the end behavior. So if you look over here, let me kind of highlight the things that we need, right? Right goes up, left goes up. We put this point on, and we need to make these zeros. Okay, so I'm going to make the left go up. So here is the left going up. Okay, we're going to come down now. I have to think, what do I do at -4? Well, if I go and I look over here at -4, I cross. So I'm going to cross. Then I have to think, well, what do I do at -1? At -1, I'm tangent, right? So let me try to draw this so that I'm tangent. Oops, I'll do that. There. That's the one for -1. Then I have to come down and hit -8, right? And then at 2, at x equals 2, I'm also across. So I'm going to come down and I'm going to cross. Now, the thing is, I don't know how low to make this go. I don't know if the graph ended up where -8 was the lowest and I went back up. I don't know if this thing passes through 8 and goes way down and comes back up. I have no clue, right? Okay, and I don't care. It's not going to change the shape. I'm not concerned about where my mins and maxes are in this case right now. So this is good enough, you guys. A little bit smoother if I can. All right, let's go in and check what this looks like when we actually see the real graph, and you'll be like, oh yeah, it's pretty good. Let's little W look, okay? All right, so let me scooch this over. Let's grab, where is it, this guy? All right, algebra. Okay, so let's go put in our polynomial. Okay. We have x plus 1 to the second. Then we have x minus 2. And then x plus 1. All right. Ooh. Turns out that's a pretty nice little W, huh? And I told you I wasn't sure how low to dip, but let's go and see if the key pieces we have. Okay, so let's go and do this in a little more detail here. Looks like this was even. I didn't FOIL it out to see that it was, oh no, it's not even. Just kidding. All right, so speed up a little bit. All right, so at -4, we crossed. At -1, we're tangent. At 2, we crossed. And this looks like this could be -8. This looks pretty darn good. And I told you guys, I was probably going to be off, huh, with how low I needed to dip on these. And I was. But you know what? Good enough. Like this one apparently should have dipped a little bit lower, huh? Okay. But whatever. Okay, we have the correct behavior at the zeros. Our end behavior is correct, and we have the correct y-intercept. Those are the key things I was telling you, that if you got that, I'm giving you full credit, okay? All right, let's try another. Okay, so let's go through those steps again so we just get used to them, kind of memorize them. So the first thing we want to do is we want to find the leading term, right? So if we multiplied this out, then we would have a negative x times x times x. We'd have a negative x cubed, blah, blah, blah. So it looks like our leading term would be negative x cubed. So that makes our leading coefficient -1. The leading coefficient, that front number, tells us what the right is doing. Since it's negative, that implies that the right goes down. Right down. Now we go to the degree, right? The exponent. If you look at the degree, it's a degree 3. Since that's an odd number, remember the two O words, odd, opposite. So that means the left will do the opposite. So if the right's going down, then the left will go up. So we got left, up. All right, let's move into y-intercepts now. So to find the y-intercept, we let x be 0. So we're going to substitute 0 in for all of our x's in the original problem. All right, 0 take away 1 is -1. 0 plus 3 is 3. So multiply those together, you get 1. A negative times a negative is a positive. 3 squared, that's going to be 9. And so this gets us 9. So f of 0 is 9, means that 0, 9 is on the graph. I'm going to go ahead and start to sketch. Let's pretend this is 9, you guys. That dot's on there. All right, let's go in and get our x-intercepts. So in other words, y is 0. Okay, so let's see here. If we let y be 0, so we're going to set x minus 1 equal to 0, and x plus 3 equal to 0. So we get +1 and -3. Now, as for the multiplicity, so the multiplicity is just the exponents, right? Oops. So this one's going to be multiplicity 1, which means, excuse me. Sorry, that's going to be a cross. I gave you some time to think. And this one's going to be multiplicity 2. Let's see if I can conjure up some sneezes again. See if you can think about what it's going to be. We got tangent, right? Even is going to be tangent. So, all right, so let's go ahead and take all of our important information and graph this guy. Right up, left up, 0, 9. And there's our zeros. Okay, so we're going to go ahead and go to +1, put a dot. -1, 2, 3, put a dot. Okay. All right, so we said that the left goes up. So we're going to draw it going up to the left, right? Now at -3, we need to be tangent. So I am not going to cross through the x-axis. Okay, I'm going to come back up. I'm going to hit this 9. Now again, I don't know if this 9's the max or not. I have no idea, okay? All right, and then we're going to come down and hit 1, and we need to cross at 1. Let me just make this a little bit higher. There we go. Okay. All right, this is +1. So let's go see what the real thing looks like. I mean, I'm close enough. Remember, I'm not going to be 100% accurate. That's why we're calling this a sketch, right? All right. negative x minus 1 and x plus 3 squared. Okay. It's not too bad. Let me just got, oops. Just got, oh, a little bit. Does look like he goes through 9. 9 wasn't the max, but I told you I didn't know that information. I don't really care. Okay, so let's see. It looks good enough. Look at that. Okay. It's pretty much the general shape. At -3, we're tangent. At -3, we're tangent. At 1, we pass through. At 1, we pass through. This looks pretty, you guys. All right. Okay, so now let's go into some that are going to up the difficulty a little bit because we don't have it already factored. So we're going to have to go in, and that's going to be step 1 is getting this, factored and get all the zeros and stuff. Okay. All right. So we can see that it has 4 terms. So I'm going to go ahead and slice it down the middle and use factoring by grouping. Okay. So from the first 2 terms, it looks like we can take out an x squared, leaving us with x plus 3. And then for the next 2 terms, we're going to have to take out a negative. We have to, okay? And you have to take something out. And this is the case where I'm just going to take a 1 out, okay? I want these to change signs. And you always have to have a number that you take out. So taking out a -1 will change all the signs. So the thing that shows up twice, we're going to factor it out. So that's going to be one of our factors. And then the leftovers, that's our other factor. Now we can go further. We see a difference of squares there, right? So that x squared minus 1 is going to be x plus 1, x plus 1, x minus 1. All right, so now we're ready to go in and do all of those things that we were doing, right? Okay. So number 1, we want to get the leading term, right? So the leading term was an x cubed. So the leading coefficient is 1. Since it's positive, that implies that the right is going to go up. So right up. Now the degree of this polynomial is a degree 3. So since that's odd, that implies that it's going to be the opposite of whatever the right was. So if the right went up, then the left will go down. All right. All right, number 2, we want to get the y-intercepts, right? Y-intercepts, sorry. Oops, so we're going to let x be 0. All right, now I like to let x be 0 in the original function instead of in the factored form. I mean, if you have to do it in the factored form, okay. But look how easy it is when we substitute a 0 in to the original. Oh, I'm terrible at zeros. All of these things that have zeros are goners. And look how fast that was. Just leaves us with the last number, basically. Anything with an x in it disappears. So that implies that 0, -3 is going to be our y-intercept. Okay, so now I'm actually going to go ahead and just do part 3 over here, you guys. Because part 3 is you finding your x-intercepts, right? So in other words, letting y be 0. So I'm going to let this y value be 0. So we're going to set each piece equal to 0. Which means we're going to get -3, -1, and 1. Now the exponents for all of these are 1s. So they are all going to be multiplicity 1, which means that they are all going to cross. So let's circle the relevant information that we're going to need to pull from this. Okay, let's go ahead and get a sketch going. So our zeros are -3, 1, 2, 3, -1, and 1. It goes through 0, -3, 1, 2, 3 on the y-axis. We know that the left goes down. So this is going to be the left, let's see, going down at -3. They're all crosses? Okay, so that's the left going down. I'm going to cross, I'm going to cross, I'm going to cross. A bit smoother. Get a little OCD sometimes, huh? Oops, it did it again anyways. Okay, all right, so that's my really shaky sketch of what the graph looks like. Let's go see what it does look like. X to the third plus 3x to the second minus x minus 3. Ooh, that was looking good. That's exactly what we want. But when it does that, for some reason it won't let me select it again without moving all the stuff underneath. Yep, fine. Sorry guys, takes me a while to get. Oh no, let's do a back arrow. Thank goodness for the back arrow. All right, let's do this again. Take 2. All right, I'm gonna move it. Find it. Aside from the shakiness, that's pretty much our graph. -3 we cross through, -1 we cross through, 1 we cross through, and down here at -3 we went through the y-axis. Spectacular. All right. Sketch the function. Now this one does not have 4 terms, so we're not going to be doing the factoring by grouping, but everybody's got an x, so we can start by pulling out an x. Now I'm noticing that this exponent is exactly half of that one. That's usually a sign that you're going to be factoring in the traditional way you do with the trinomial, where you look for factors of the last number, things that multiply to make the last number, and add to make the middle number. So let's see here, what would that be? -4 and -1, you guys? Let's see. -4 times -1 is 4. -4 plus -1 is -5. Now, in the traditional way, normally we'd say x minus 4 and x minus 1. But hopefully you're seeing why that's not going to work. If I multiply x times x, I'm not going to get x to the 4th. I'm going to get x squared. So that's why we have to up the exponent on this to both being squareds. So now when I multiply, I get that x to the 4th. And if you continued to FOIL it out, you would get that x squared in the middle, okay? All right, so now those are looking too good. I mean, you're like, I must have done something right, because we got 2 difference of squares here. So that x squared minus 4, that's going to be what? X plus 2, x minus 2. And that x squared minus 1, that's going to be x plus 1, x minus 1. I am just putting all kinds of straight marks on here. There we go. Okay, so let's go in and get all the things that we need. So number 1, we're going to need the leading term, right? And that's going to be x to the 5th. So since the leading coefficient is 1, which is a positive number, right? Then that implies that the right will go up. So right up. Then we have a degree of 5. Odd implies opposites. Those 2 O words together. So if the right went up, then the left will go down, right? Left down. All right, so now we're going to get the y-intercepts by letting x be 0. And I'm going to do that in the original because that'll be a 2-second problem. If we substitute zeros into all of these x's, then that means the whole thing's going to go to 0. The whole thing is going to get annihilated because everybody's got a 0. So that means the whole thing is going to be a 0. So that implies that 0, 0 is going to be our y-intercept, which means it's also our x-intercept too, because 0, 0 crosses both the x and the y-axis, right? So we already found one of our x-intercepts too. So for the x-intercepts, we let y be 0. And we want to do that on the factored version, not the original. So I'm going to go 0, and let me write out all those factors we worked so hard to get. So if we set each piece equal to 0, let's just go for it. You guys know to change the sign. So that one will be a -2. This one will be a +2 when we move the 2 over. This one will be a -1. And this one will be a +1. Holy cow, we had a lot of zeros. They're all multiplicity 1s, which means that they are all going to be crosses. So multiplicity 1 implies we have a bunch of crosses here. All right, so let's go ahead and graph our relevant info here. Right up, left down, 0, 0. And we're going to mark all of these guys. Well, let me make that bigger since 2 is the biggest this goes. Okay, so we have a 0 at 0. We have a 0 at 1, at 2, -1, -2. The left goes down. So here is me having, oops, the left go down. Now, something that I want to point out, I think this is number 6 or 7 on your guys's, it's 6. All of the exponents of the original problem are odd. We got x to the 5th, x to the 3rd, x to the 1st, right? So let me just kind of, I'm going to rewrite that right here. This is an odd function. And I'm going to write down me circling all those exponents. So why is that important? So that implies that this is going to be symmetric to the origin. So as I'm graphing this, I know it needs to look the same right side up as upside down. So however high I go here, and however high I go here, and I don't know how high to go, you guys, to be honest, but I need to keep those heights the same. Oh my goodness. Because I want this to look the same right side up as upside down. Okay, so I did my best to try to create something that looks symmetric to the origin. In other words, you know what? I don't think I need to screenshot. I think I can just select it. Let's see what that does. Yes, if I look at it like this, I flip it and I go like that, it should look exactly the same. Okay. Again, I didn't know how high to go. Like maybe this is the one higher than this one did. I don't know, you guys. We'll find that out right now when we go and we get the genuine graph. And you'll be able to see the symmetric to the origin so much better when you see the one from graphed in GeoGebra. X to the 5th minus 5x to the 3rd plus 4x. Oh, wow, that's nice. Okay, let's get that out of there. Let's bring it over here. And, so let me shrink this guy down. Here. Now look at this. Right side up, it's got this little hump and then big hump. I'm gonna Same exact thing, right? A little hump and then a big hump. That's totally the technical terms. All right, so there's no difference between this right side up or upside down. And we have the proper behavior. We pass through -2, -1, 0, 1, 2. The right goes up, the left goes down. This looks pretty darn good. All right, you guys. So that's our sketching of polynomials. All right, so let's go ahead and we're gonna do some more sketching, some matching at the end, but for now we're gonna go ahead and cover this new topic, the intermediate value theorem. The intermediate value theorem is actually more generalized than this, but we're gonna give you something that's good enough for college algebra, and we'll expand on it in calculus and make it a little bit more complex than it is here. So it says, let f be a polynomial function. Now, the reason why they say that is because we need a continuous function, and that's what polynomials are. Polynomials, you never lift your pencil, right? There's always on a parabola, you never lift your pencil, on a line, you never lift your pencil. So we're looking at continuous functions. So that's a polynomial for sure, okay? There's others too, but polynomials are definitely continuous. Now for a less than b, if f of a and f of b, so I try to draw things so I can understand it. When they say a is less than b, I don't know if it's an x or a y, but now that I read this part, I do. F of a and f of b are definitely y values. And remember, it's f of x. So if it's f of x, whatever's in the parentheses is always x. That tells me that a and b have to be x values. So I'm going to draw. And I'll just do it in quadrants over here, the positive x-axis side, so it's a little bit easier for us to digest. Okay. Now I placed it so that a is less than b because that's what it says right here. And I know that they're x values, so I placed them along the x-axis. Now it says f of a and f of b have opposite signs. So one of them is going to be positive and one of them is going to be negative. Now I don't know who. Let's just say that f of a is positive. And then we'll go ahead and say that f of b is negative. So I'll put it somewhere down here. Okay. All right. Then f has at least 1 0 on the interval of a to b. Okay, so at least 1 0 on the interval of a to b. Well, yeah, it's a polynomial, which means I don't lift my pencil. So for me to connect these two dots with each other, I have to cross through the x-axis at some point. And where do I cross through it? On the interval of a to b, somewhere in between a and b. Now it could be that they say at least, we don't know, maybe this went like boom, maybe it crossed multiple times, right? Okay, but it's got to have at least one. So let me see if I can put back up what I had a second ago. Put it back up. No, okay. So what I'm going to do, let me take a picture of this. Shrink it down. And I'll show you 2 examples. One where the first one I showed you, where it just crosses through and has 1 0 on the interval of a to b, and one that has multiple zeros, right? And then this one they use at least 1, right? Okay. All right. So it's not, these theorems, if you really think about them, a lot of times they aren't super complex. And I mean, this isn't. It's like, hey, I got somebody above the x-axis. I got somebody below the x-axis. I'm not allowed to lift my pencil. Okay, I have to cross through the x-axis is essentially what this is saying. So let's go in and go ahead and apply the intermediate value theorem. Show that f of x has a 0 on the interval of -1 to 0. So what we're going to do is we are going to substitute -1 in to the function. I'm just going to let my calculator do it because that's what I have a feeling most students would do. So I'm going to try to model that, okay? All right, so we're going to go ahead and put parentheses. Don't forget the negative sign is different than the minus sign. Oops, on a lot of calculators. I think this one, it might let you get away with it. All right, to the third, right arrow to get out of it, minus 13 times negative 1 squared this time, plus 33 times negative 1 plus 35. Negative 12. Let me just double check because I did do these earlier, so I want to make sure I'm getting the same stuff. All right, cool. All right, so now we're going to go in and we're going to substitute in 0, the other endpoint. So I'm using these interval endpoints to substitute in. So we'll have 0 cubed minus 13 times 0 squared. That's 33 times 0. And we don't need a calculator for this. The zeros will all get annihilated, and that just leaves us with 35. Okay, so the picture. It's always important to have the picture. When x is 0, the y value is 35. So here's a point. When x is, negative 1, we probably should have, there we go. When x is negative 1, the y value is negative 12. Let's say that's negative 12. So come over here, bam. All right, so 0, there's a point 0, 35 that we graphed, and there's a point negative 1, negative 12 that we graphed, right? Okay. All right, that's exactly what we want because one's positive and one's negative. So that means we'd have to cross through the x-axis on the interval of negative 1 to 0 in order to connect those dots. So that's kind of our picture. Now, I don't know if it looks exactly like that. It doesn't say show how many zeros, it just says show that it has a 0. So we're going to go ahead and say, since f of negative 1 and f of 0 have opposite signs, and f is a polynomial, right? And yeah, I'll do fine. And f is a polynomial, which means it's continuous. I almost feel like I want to get rid of that. I don't know my English very well, whatever. Let's see here. F has at least 1 0 on the interval of negative 1 to 0 by the intermediate value theorem. That's going to be our answer. Okay. So make sure you show the math over here so that you show that they do have opposite signs. And as long as the teacher sees that they have opposite signs and then you make that claim here, then you're good. Okay. All right. Now, at least one. I'm curious what this graph looks like. Let's go check it out. See if we were right on that. Okay. So then actually let me switch this guy over. Perfect. Okay. So let's go put this polynomial in. It's x to the third minus 13x to the second, 33x plus 35. All right, now we said that it's going to have at least 1 0 on the interval of 0 to negative 1. Wow, that is so perfect. Look, here's the interval of negative 1 to 0. There's our 1 0. Let me just, before I take a picture, and bring it over to our notes of the actual thing. Let me shrink the y-axis down a little bit. Where's the part that we care about? We didn't have to find all of the zeros. We just had to find on the interval of negative 1 to 0. So I'm going to put those side by side. Look at that. We almost have the right spot and everything. Yeah, looks good. All right, let's try another one. Maybe I won't get the pictures this time. We'll just go through the motions, okay? Using the intermediate value theorem, determine, if possible, whether the function has at least 1 0 between a and b. So we know the deal here. We're going to substitute those values into the function. So we're going to substitute negative 1 into the function. So let's go and see what f of -1 is. I'm getting -5. Alrighty. Just take a look at my notes because I got +6 before when I did this. So let me go see what I did on the calculator. Oops, I forgot a 6 right here. All right. So it's parentheses -1 to the third plus -1 squared minus 6 times -1. There it is. Okay, so I knew I did. Good thing I do these ahead of time. I know myself. I'm like, you know what? You're probably going to make some mistakes. So let's put this in here. All right, so -1, 6 is on the graph. All right, let's go in and substitute in 3 this time. So we have to do 3 cubed plus 3 squared minus 6 times 3. Oh, you know what? I think I got the wrong function somehow. Okay, looks like I'll have to do it again. You can tell I don't use the calculator often. When I went through my math program, we weren't even allowed to use it. And so I'm just like, honestly better by hand. But I know nowadays they start handing the calculators out pretty young to students and allowing them and stuff. So I'm just trying to roll with what you guys would do. All right, so I got an 18. Okay, so that implies that 3, 18 is on the graph. Okay, this is not good. They both ended up being positive, right, you guys? Uh-oh. That's not what the intermediate value theorem says. It says if they have opposite signs. Now, this doesn't mean that we can conclude that there isn't a 0. This means that the intermediate value theorem doesn't apply. Remember with the theorem, if the ifs have been met, then you're allowed to use the then part. Well, ours says if they have opposite signs. Well, they don't. Okay, so then I can't use the theorem to say anything. Okay, so be careful that you don't say it doesn't have a 0. Okay, we don't know anything now. Okay, so since I'm going to say, use math language, hypotheses have not been met, we cannot use the intermediate value theorem to conclude anything. Before I do that, though, let me type in a little, let's make this a little bit larger, you guys. All right. I do want to make a comment, about there being, notice f of -1 and f of 3 have the same sign. They are both positive. So since the hypotheses have not been met, we cannot use the intermediate value theorem to conclude anything. Let's go to a picture because a picture just makes all this make sense. Okay, so we've got what, -1 and 3. Let me give you a couple examples of things that could happen. So let's say this is -1, and let's say that this is 3. Well, they both ended up being positive. This one goes through 6, and then this one is 18. Now, we can't say that it does or doesn't, because maybe it just goes straight there, and I don't have a 0. I never cross the x-axis, so no zeros. But what we really know is nothing, okay? I mean, maybe it does. Let's say this is 18. Maybe it did for some reason do this. We don't know, so maybe it does have zeros. What we're saying is We don't know, okay? The intermediate value theorem does not apply. All right, so let's go ahead and check this next one. Got to throw some fractions in, right? Make sure our skills are up to par. Can't be ignoring these guys. All right, so we're going to substitute in -1/2 into the function. So let's go see if I can actually use the calculator correctly here. Clear this out. All right, so we've got 1/3, right arrow, parentheses, -1/2, right arrow, parentheses, to the 4th, minus -1/2. Oops, I guess I do that, huh? To the 3rd. What do I feel like? There we go. Enter. All right, I got, let me just make sure it looks good. It does. So it's 7/48. Positive is all I care about. Now let's go in and substitute in this time a +1/2. And so I did a negative, didn't I? Hello. A +1/2 this time. Let's see what it does. Okay, I think I can hit the up arrow. Oh no, okay, let me just hit to the right. There we go, that's what does it. So backspace, let's get rid of those negatives, right? Backspace equals -5/48. Cool, and this is what I got when I did it myself, so this looks good. Okay, so we are in business. We got opposite signs here. Perfect. All right, so let's go ahead and write our statement out, okay? Since f is a polynomial, therefore continuous, and f of -1/2, oops, let's keep those together, and f of +1/2 have different signs, we are guaranteed at least 1 0 on the interval of bracket -1/2 to 1/2 bracket by the intermediate value theorem. Intermediate value theorem. There we go. All right. So that's a pared down version of the intermediate value theorem, but it's good enough for what we're doing here, especially because we're talking about polynomials. So we might as well state it that simply. All right, you guys. So here's just a little matching. So we'll finish up with trying to quickly pick out a graph given a polynomial. So something that I'm noticing is that the leading term is -x⁴. So since the leading coefficient is negative, that implies that the right will go down, right down. Also, since the degree is 4, and that's even, then that implies odds opposite evens the same. So the left will also go down. And something else that I kind of eyeball besides the right goes down and the left goes down, the last numbers are y-intercept. Because remember, to find y-intercepts, you let x be 0, right? Well, if we substituted zeros in for all of these x's, the only thing that would survive would be the 5. So I'm looking for something that goes through 0, 5 also, okay? So let's see here. The right goes down. The left goes down. So let me highlight, that could only possibly be 2 possible things. These are the only 2 where the right and the left go down. But this is the only one that goes through 0, 5. So we're going to go ahead and say that the answer for this one is going to be H. All right, so H is out. We got that one. Cross them off. All right, let's go to this one. We're gonna do the same thing. Well, I mean, you can tell that this is a parabola that faces downward just from that, right? X squareds are always parabolas, and it faces down from the -3. Faces down since a is less than 0. And there's only one parabola that faces down, right? That was quick, huh? D is the only parabola that faces downward. Okay, so H and D are out of here. All right, let's go to the leading term test. So the leading term is x to the 4th. Since the leading coefficient is 1, which is positive, then that implies that the right will go up. Right up. Since the degree is 4, which is even, that implies that the left will do the same, right? So that means that the left will also go up. So left up and right up, that narrows it down to not that one, hello, either this one or this one, right? I think we can tell it's not a parabola, so it's probably not going to be G. But let's go in and check that y-intercept again. Okay. So remember the y-intercept, is when is the last number, right? The y-intercept is when x is 0. And that's simply always going to be the last number. So the y-intercept for this problem is going to be -4. So 0, -4. Well, if you look at, we picked these two graphs. No. Oh, I didn't even look at C, huh? We picked these 3 graphs. Those all go right up and left up. But the only one that goes through -4, 0, -4, is J. That's the only one that hits -4. So J is the winner. Okay. All right, so let me just erase these guys so I don't confuse myself. Okay. All right, so H, D, and J are out. H, D, and J are goners. All right. Well, this one is a line. It's clearly a line. It's in y equals mx plus b form, right? So there's only 2 lines up here. And it can't be F because F is just a horizontal line. Okay, so I might as well just type this out. There is only one line with its negative slope. All right, the slope is -2/5, you guys. So remember, negative slope means that it slants towards the left, right? So somebody would be going from left to right, they'd be going downhill. Okay, so it looks like it has to be B for that one. So B, H, D, and J are gone. B, D, H, and J, sorry, we're gone. Okay. For this one, its leading term is x cubed. The leading coefficient is 1, which is positive. So that tells us that the right is going to go up. The degree is 3. Odd means opposite. So if the right went up, the left will go down. So let's look for ones where the right goes up and the left goes down. So it's between those two. I bet you the y-intercept will help us. So remember, for the y-intercept, we let x be 0, and I've been saying it's the last number. This one's kind of tricky. I mean, not really once I show you. If we plug a 0 in, everything's going to go away. So that means that this graph passes through 0, 0. So of those two, the only one that goes through 0, 0 is A, right? So A must be our answer. So I'm going to take I off of there. So A, B, D, H, J are gone. A, B, D, H, and J are gone. We're almost there, you guys. I think I almost want to say this has to be I, but let's go in and check, okay? All right, so the leading term is x to the 6th. The leading coefficient is 1, which is positive. So we know right up. Right up. So it can't be E. So it's looking like it's I, because we know G is probably going to be a parabola. But let's go in. The degree is 6. Since it's even, it's going to do the same. The left's going to do the same. So if the right went up, then the left goes up. Left, up. Okay, so the right is up and the left is up. Let me just double check everything here. And it goes through 0, 0. Oh, I didn't even see C, you guys. There's the winner. All right, the right goes up, the left goes up, and it goes through 0, 0. C is the winner. I don't know how I missed C on that one. All right, so pretty much the East is still left, right? In that row. These are all gone now. And then the other row, H and J are gone. Okay. All right. The leading term is x to the 5th. The leading coefficient is 1, which is positive. So the right goes up. So it's got to be I or G. All right, and the degree is 5, which is odd opposite. So that means if the right went up, that the left will go down. So right up, left down. Well, there's only one left where the right goes up and the left goes down. On this one, the right goes up and the left goes up. On E, the right's going down. So it looks like it has to be I for this one. We don't even need the line interceptor, guys. So E, F, and G are the only ones that are left. Is J still up? Awesome. All right. The leading term is negative x cubed. The leading coefficient is negative. So that implies that the right will go down. Right, down. Well, the only one where the right is going down that's left is E. So it looks like it would have to be E for that one. On G, the right is going up, and then F is just clearly not the right graph. So F and G are the only ones we have left to choose from. Okay. Well, this is a parabola because it's an x squared. This is an upward. You know what? I might as well type because, man, my writing. Whew. So this is an upward facing parabola since A is positive. Okay. So since A is greater than 0, faces up, so that has to be G. So by default, it looks like this last one has to be F. And that's pretty clear, you guys, that this is just going to be a constant or horizontal line. Okay. So this is a constant. So it's a horizontal line. Oops, forward. All right, so it has to be F. So that's not bad. We got away with doing most of them. I'm sorry, you guys. Oops. We got away with doing most of them just by the leading term test, huh? So not too shabby. All right, you guys. So that's how we're going to graph polynomials. We don't need 100% accuracy, just the general shape and some key things like the end behavior and how we behave at the zeros and stuff. All right, guys, take care.